So I think to a non-homogeneous VDE, a particular solution can be expressed as nothing more than my fundamental matrix times some other vector u bar. Oh, you guys, sorry, I just made the u bar notation up out of thin air. Where u bar has a quality. I said u bar has a quality that if you differentiate, multiply on the left-hand side by the fundamental matrix, you're going to get your b bar. Do you guys remember what the fundamental matrix is? I mentioned it when I started talking about theory of VDEs, but we never used it.
No.
The fundamental matrix is nothing more than the matrix where column by column I've got solutions to the corresponding homogeneous VDE. That's all it is. And today, I would like to see if I can get through maybe 2 examples of non-homogeneous VDEs. The first one will be a 2 by 2. Well, sorry. The first one will involve a 2 by 2 matrix A, and the second one I'll try to grab a 3 by 3. But I think there's a lot of work here. So, everybody, jumping in. My first example. Let's solve this VDE where I've got a specific matrix A and a specific matrix B. And you guys, today in class, I'm not going to get to the point of giving you guys any applications, so I'm sorry, but today I'm going to be abstract, algebraic, purely mathematical, and then we'll put this to practice. And I did make up an example. I have an A being 7, -1, 9, 1. So 7, -1, 9, 1, and let my B bar be this. So I think just like with standard differential equations, I have to break this up into cases. Let me first take a peek at the homogeneous case. And in the homogeneous case, I really want to solve the underlying homogeneous VDE. Now to do that, I don't know what I typically do. Eigenvalues first. Eigenvalues. And to come with eigenvalues, I will subtract lambda off of the main diagonal. Does that give me lambda minus 7, you guys, times lambda minus 1? By the way, you guys, I may have written this example, but I don't have the answer. I only wrote the question down. So let's see how nice it turns out. Minus the product down the main diagonal, the non-main diagonal, being equal to 0. That gives me a lambda squared minus 8 lambda. Is that plus 16? Is that factorized? Yes.
Mm-hmm.
Now,
4 and 4, so it's
minus
perfect
4
square.
twice, I only get one eigenvalue. And since I've only got one eigenvalue, let me come up with the corresponding eigenvectors. And for the eigenvectors, I guess it's going to give me, well, let me subtract the 4 off the main diagonal. Does that give me 3, -1, 9? I said 4, didn't I? -3. And I'll augment with the zeros. And I think that merely gives me this. That being the case, I think the corresponding eigenvectors, I'll call them, how about just a single one, sorry, I'll slow down. A corresponding eigenvector, I'll call it V1 bar. I will write as nothing more than, you guys, what's an easy one? Give me a really easy one. 130. It's a nice one. But of course that means this. It means my x1 bar t is going to be nothing more than my eigenvector 1, 3 times e to the, is it a 4t? Now let's take a peek at the non-homogeneous case. What was that?
Yeah.
Good, I can't jump. As a matter of fact, I only have one solution to the homogeneous VDE. I've got to generate a second one. But of course, in this particular example, my matrix A is defective. Since it's defective, shoot, I've got a bit of work to do. I think then to find a second linear independent solution, oh man, it started on the wrong side of the room. Jeepers. I think to find a second linear independent solution to the homogeneous case, well, you guys, I'll just make one up out of thin air. Let's think of x2 bar t as being nothing more than, I don't know, how about another vector v2 bar plus t times v3 bar. times my e to the 4t, where this particular solution is going to have to satisfy the original vector differential equation. Well, maybe not the original one, I meant the underlying homogeneous vector differential equation. So picking this up off the board, slapping here and differentiating, I've got the first as is, times the root of the second, plus the second as is times the root of the first, being equal to nothing more than my matrix A times my solution x2 bar, which is this. Is that plus b bar t, guys? No, no. Remember, I'm just trying to find a second linear independent solution to the homogeneous VDE. So I'm not considering b bars yet. That being the case, I will dive in and solve for my gosh, what am I looking for? I forget.
Why do you ignore B?
Because I'm still in the homogeneous case. As a matter of fact, in the non-homogeneous case, it's really got to be the case that I generate the fundamental matrix first. So I need those two linear independent solutions to the homogeneous VDE. Well, I'll come back then. I'm trying to solve for V2 bar and V3 bar. To do that, let me equate coefficients. And equating coefficients of t, I think what that's going to give me is the following. Actually, I have no idea. Is that a 4 times V3 bar? You guys, can I drop the e to the 4t's at this point? Being equal to, on the right-hand side, would that be an a times V3 bar? So a times V3, oh, you guys, look at that. That just screams out at you. The V3 bar is an eigenvector corresponding to the eigenvalue of 4 for the matrix A. And you know what? I've already got one. So I will choose my V3 bar to be nothing more than my 1, 3.
Wait,
Yes, I'll wait.
was that only coincidental, or?
It's definitely not coincidental. Whenever you equate the coefficients of t, you will come up with an eigenvector. Now, I was kind of rushed yesterday in class when I introduced this. Personally, I don't usually do it this way. What I typically do is I'll call V3 bar 1, 3 with an R up front. Some multiple, just in case it makes my arithmetic easier later on. But I ran out of time, so I just did the heck with it. Let's take the shortcut. I'll always call it this. It just might introduce fractions. And I think equating constants. I think what this is going to give me is, again, I don't know, you guys. Can I take a peek? Dividing both sides by the exponential factor. Is that a 4V2 bar plus V3 bar being equal to A times V2 bar? You know, I know we're coming to the end of the semester, but I'll say it again. You're paying money to be here. You tell me if I'm skipping too much. But bringing all the V2 bars to one side, factoring it out, wouldn't that give me an A minus 4I times my V2 bar being equal to V3 bar? Where my V2 bar is I don't know, I'll give it a name. I'll call it, how about V1, V2, without the bars. Now, if I rewrite this vector equation back in matrix form for system equations, I think that gives me the following. Subtracting 4 from the main diagonal from A, I have no idea what that would be. Is that going to give me a 3, negative 1? Is it a 9, negative 3?
No,
Well, where's my mistake?
it's not equal to
Augmented
0.
Oh, yeah, I don't have zeros on the main diagonal.
Yeah, and then for I guess your B or your augmented matrix, you need to plug in B3 rather than just 0, 0.
Thank you. That's where my mistake is. I think I've got to augment with a V3 bar, which I've already declared to be 1 and 3. It was kind of nice. No fraction. Well, maybe they're all. We'll check it. I do think this reduces somewhat to this augmented matrix. The second row, in other words, is simply multiple of the first. But I think what this tells me, in terms of a single equation in V1 and V2, is that 3V1 minus V2 is equal to 1. So if we let V1 be equal to 0. I think it says that V2 is equal to negative 1. You guys, I've got the mathematical right to let V1 or V2 be anything I like, as long as in the end, the corresponding vector is not the 0 vector. That being the case, I guess now what I have, I'm sorry to erase that beautiful proof. So I guess what I have at this point is that my V2 bar is nothing more than, I've lost it, is it 0, negative 1?
Yep.
Ah, but that means my X2 bar T is going to be nothing more than, check out this up over here, you guys. My V2 bar.
Professor,
Yes,
when you augmented the matrix right there, where did you get that from?
the 1, 3. I did this. First things first. Look at how the right-hand side of the equal sign is just V3 bar, which I already found to be an eigenvector. That's where the 1, 3 came from. Now on the left-hand side, doesn't this amount to having V2 bar be multiplied by A minus 4? Okay, you see it. Just subtracting 4 along the main diagonal. Okay?
So V2 bar I think should be 0, negative 1.
Thank you very much. That's what I had written. I didn't write it in. And because of what you see right here, I think my X2 bar T is going to be nothing more than my V2 bar, which is this, plus my T times V3 bar, which was one of my eigenvectors, all times my exponential factor. Is it 4? Or shall I say, I simply have a T and a negative 1 plus 3T times my e to the 14. Oh, by the way, you guys, this means a couple of things. Number one, you guys, can I change this a little bit? I won't change my symbols. Can I just slide it up a tad bit? Just give myself a little bit more room. So just sliding up a tad bit, I just said, this is equal to my t negative 1 plus 3t is exactly what I had written before, e to the 14. It's just that. My complementary solution then is simply going to be C1 times the first. Is it 1, 3? Plus C2 times the second, which is T negative 1 plus 3T. Oh shoot, I forgot my exponential factor. I'll pull it out. It also happens to mean, though, that my fundamental matrix is going to be a matrix which, column by column, simply consists of my complementary components, which I think are going to be G for 7, e to the 4t, and 3e to the 4t, and then a t e to the 4t, and then a negative 1 plus 3t e to the 4t. Oh, by the way, you guys, if you think this solution and this one were not linearly independent, what would you do? What would you do? No, you wouldn't. You just pull out of your back pocket the answer, the Wronskian, and check the Wronskian. As long as it's non-zero for some value t in your interval, whatever the interval is, then you know you got independence. By the way, and that's a big term. Well, I guess all the work I've done in these 3 ink boards is just to find the complementary solution, and now I need to dive in and look at the non-homogeneous case, Chris.
Just a really subtle question about
The fundamental
the
matrix.
notation for the fundamental matrix. Is it
It looks
Roman numeral x, or is it 2 bars?
No, you know what? That's a good point. This is a lowercase x bar.
Okay.
And with my fundamental matrix, I typically use an uppercase X and just put slash on the top and bottom. It's not a bar. To me, the bar is kind of elevated. And so I meant to slash up through the 2 points on the X's upstairs and downstairs. You know, technically speaking, if I were a textbook, I don't have to do this kind of stuff. I can just boldface an uppercase letter X. I just can't boldface the board. Well, I think that jumping into part 2, looking at the non-homogeneous case, I think my XP bar is going to be, remember, I'm just trying to find one particular solution. I think my X of P bar is going to be my fundamental matrix times my U bar where? U bar has a quality that if you differentiate it, multiply it by the fundamental matrix, you're simply going to get your B bar right back. That being the case, let's dive in and find it. I don't know, you guys, I guess I got a question for you. How do you install this system? Do you use inverse matrices? Something else?
Just use Gaussian elimination, right?
All right. And if I use Gaussian elimination, wouldn't I get this?
Or in this situation, maybe you just use MapD.
You know what, this is what my B bar looks like. What is my B bar?
2e to the t and e to the t.
Because I don't know if it really matters that much, to be honest with you. Whether it's Cramer's rule, inverse matrices, augmented matrix, just because it's a 2x2 matrix, that's the fundamental matrix, I don't think it makes a difference. I think all the work's going to be pretty easy.
Say it were a 3x3 though.
Oh,
what
now
would-
that way I might want to be a little more selective in what technique.
So what would you use for a 3x3? Gaussian?
I think so.
Okay.
I think that'd be my preference.
So we should probably just stick with Gaussian, just to
I can't-
maintain
I'm just a
consistency.
professor. I can't say that
Yeah.
because when I've graded your exams already, I see some people really prefer to use Cramer's rule whenever they can.
Yeah.
So it depends on your preference.
Okay.
I maintain I don't care which way you do it. Makes my life miserable at home when I grade your papers, but I can't object. I can't object. You guys, can I start over? I'm getting too big. I'm really worried about room. So may I? I just try to write smaller. So I meant to say, if you want me to use an augmented matrix technique with Gauss-Jordan elimination, I got e to the 4t. T e to the 4t. How about a 3e to the 4t, and then a negative 1 plus 3t times e to the stuff. I forgot my t. Jeepers. And then I'll augment this with, is it 2e to the t? And then a single e to the t. So let's reduce. I think, I don't know, you guys, when I reduce, how do you want to do this? Be honest. I could.
Yeah, divide out e to the t first would be the best. On both of them.
If you insist, you know what I was thinking when I wrote this down before? And again, I'm being honest with you guys, I did not solve this system, I really didn't. But just glancing at it, I was thinking, oh, the heck with it, at least now leave it as the way it is. If I multiply this by negative 3, add it to the first, I think a lot drops out. So allow me not to mess with the e to the 4t in the first row, first column. Let me just multiply the first row by negative 1 in my head, which means officially right now it's not changing. And let me just multiply the first row by negative 3, add it to the second. I think the first term in the second row completely drops out. I think something really nice in the second column, second row, pops up. And I think even over here, I just get a negative e to the t.
Now divide out e to the t.
I couldn't
Oh,
really-
no, well, no, you can, yeah, you can add the second row to the first row and,
God, I'll do just that. So you're saying multiply...
oh wait, no, there's a factor of t there that I wasn't seeing, yeah.
Well, that's okay, that's okay. I
Okay.
still think it's a good way to go. I think maybe I prefer to not officially change the second row. I said, not officially change the second row. I'll listen to what I'm saying. By the way, Brad,
That's your battle guy?
that's E, not a row.
Oh, okay, I thought it was a row for a minute.
The second augmented matrix, the second row, it should be negative 5 e to the t, because if you multiply negative.
Thank you very much. I've already committed an arithmetic error. Remember, I was multiplying the first by negative 3 added to 7. Doesn't that give me a negative 5 of these? In my head, I just had negatives of this plus this. And I've got negative e to the 4t. You guys, I got into so much trouble in my last class. Help me with this. What's that symbol? See?
No,
I got
no,
it.
but you weren't even writing it like that. That's how you ended up writing it. You were just drawing an E. Yeah, that's
It was
an E.
not an E.
That's
That is not.
Can you tell that row?
It's kind of a row.
I saw it. All right, never mind. Leave it alone. Jeepers.
Using handwriting analysis.
What's that?
I said using handwriting analysis.
So everybody, to eliminate this term, I'll multiply the second row by a positive t, add it to the first, use the result of my new first row. So I can read this. I said multiply the second row by t. That's going to give me a 2 minus 5t, e to stuff.